In our next example, y is going to equal the natural log of x over 2x. Again, we want to find the critical values for f prime, so that will give us the inflection points and the concavity. Okay. Again, we start out the same way, so we need to find our derivative. Okay. So here, if I'm looking at y prime, this one's going to be a quotient rule. So derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Okay. Again, we definitely want to clean it up before we try taking a second derivative. So here we can see this is going to be a 2 minus 2 ln of x all over 4x squared, which we can pull a 2 out of, so 1 minus ln of x over 2x squared. Okay. For our second derivative, okay, same thing, it's a quotient rule again. So derivative of the top, which is going to look like a negative 1 over x, times the bottom minus the top times the derivative of the bottom, all over the bottom squared. Okay. Again, we'll clean it up. So we'll get a negative 2x minus a 4x plus 4x ln of x all over 4x to the fourth. Okay. Here we notice 2x is common in every term. And we can actually combine these terms if you like. But pulling out that 2x, well, let's combine first. So we're looking at negative 6x plus 4x ln of x over 4x to the fourth. Now we can pull out the common term of 2x from the top and bottom. So we'll get negative 3 plus 2 ln of x all over 2x cubed. There's our second derivative. Okay. Now from our second derivative, we need to find where it's undefined and where it's 0. Okay. Now this one, it is good to note that we have a natural log in here. And the domain for our natural log function is 0 to infinity. So we know that we're not going to have anything less than 0 in this problem. Okay. So y double prime is going to equal 0 when basically the numerator is equal to 0. So negative 3 plus 2 ln of x equals 0. Okay. So here we can see 2 ln of x is going to equal 3, or ln of x equals 3 halves, or x will equal e to the 3 halves. This will be undefined when the bottom of our function is 0. Okay, so again, nice thing about rationals there. So here this is just going to be at x equals 0. Okay. Now note x equals 0 is not in our domain. So even though it's one of the critical values for this function, it doesn't make sense in the function because our function's undefined at 0. So here, when we go to our number line, the only value we have to worry about is this x, e to the 3 halves. Okay? And we want to test some points. So e, again, is about 2.71 to a positive power, or power bigger than 1 means it's growing. So 1 is certainly a good number to try over here. And if you don't have a calculator, again, if I'm looking at about 2.7 to the 1.5 powers, well, I know that's definitely going to be less than 10. Okay? Because e squared is almost 8, or a little bit around 8. So there's 2 test values. Again, we're plugging these back into the derivative. So there's the top of it, there's the bottom. Back over here is our whole function. At 1, Notice natural log goes to 0, so we have something negative over something positive. So that's going to be a negative value. And then if we look at 10, well, 2 ln of 10 is going to be bigger than 3, so that's positive, and then on the bottom it's positive. Oops. Okay. So here we have that it is concave down from negative infinity to e to the 3/2. It is concave up from e to the 3/2 to infinity. Oh, and that's wrong. Remember our domain here. Okay? So remember our domain is strictly greater than 0. So for this concave down, we need to say from 0 to e to the 3/2. And then lastly, our inflection point for this one is going to occur at x equal e to the 3/2. Again, if we want to find the point, we can take that value and plug it back into the function, the original function, to get the y value. Okay, let's look at one last example. Y equals 21x plus 40 over 6 times x plus 3 quantity squared. Okay, so the same thing, we want to find the concavity and the places where we have inflection points. So again, for this, we're going to start with our derivative. Okay, again, here, our derivative is going to require a quotient rule. But notice in the denominator, I also have a power, so it's also going to have a chain rule in there. Okay, so y prime, derivative of the top, is going to be 21 times the bottom minus the top times the derivative of the bottom. All divided by our bottom squared. Again, we definitely want to clean up before we try to simplify. So notice here I've got an x plus 3 in every term. I can pull that out. I also have a 6 in every term, so I can pull that out. So we'll have 21x plus 3 minus a 21x plus 40. That times 2 all over 6x plus 3 cubed. Okay, simplifying the numerator, we see 21x plus 63 minus a 42x minus 80. Combining like terms, we get a negative 21x minus 17 over 6x plus 3 cubed. Now we want our second derivative. Okay. Okay, so y double prime, same thing, it's going to be another quotient and chain. So the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Okay. Again, we can pull some things out. So again, we'll have a 6 and an x plus 3 squared in every term, so we can pull that out. So we get a negative 21 x plus 3 minus a negative 21 x minus 17. That times 3 6 x plus 3 to the 4th. Okay. Again, multiply out. So negative 21x minus 63 plus 63x plus 51 all over that common denominator. Combining like terms, we'll have a 42x minus 12 over 6x plus 3 to the 4th. Okay. Here you can notice there's a 6 in every term, so I'm going to go ahead and just take that out, and we'll have a 7x minus 2. Okay. There's our second derivative. Okay. Now with the second derivative, again, we want to find the critical values. So we're going to look at when y double prime equals 0, which will happen when the top is 0. So 7x will equal 2, or x equals 2/7. And when it's undefined, that'll happen when the bottom equals 0. Okay, and here we can see that's going to happen when x is negative 3. So on our number line, we have a negative 3 and a 2/7. And so we can test points. 0 would work between them. 1 on the positive side, negative 5 on the negative side. Plugging these into our derivative, second derivative. So at 1, we can see the top is positive and the bottom is positive. At 0, bottom is still positive, but the top is negative. And at negative 5, we get a negative on the top and a positive on the bottom. Okay. So we have that it is concave up on the interval from 2/7 to infinity. It's going to be concave down from negative infinity to negative 3, union negative 3 to 2/7. And our only inflection point, again where it changes sign, is going to be at x equals 2/7.